Hey everyone. If you notice, I'm standing in front of a different board. It's a whiteboard in this case. I'm in building 26. That's the graphic communications or graphic arts building. I reserved a room here. I'm going to give it a shot. There's definitely more room in here, but it's a little echoey, and I have a feeling that the chalkboard actually is going to show up better than a whiteboard. So I'm going to try this lecture. I will post this lecture. Let me know what you think, and I'm going to review it and see whether this is worthwhile to film in here or just to stick with my office. I'm actually kind of getting comfortable just staying in my office now. All right, so let's get started today. So far, we've studied linear systems, we've studied matrices, and that's comprised, I guess it's been section 1.1 up through 1.7. We're starting section 1.8 with this lecture right now. And so the first 7 chapters or sections of the first chapter give you the impression that linear algebra is all about the study of linear systems and matrices. Okay, linear systems and matrices play a very important role in linear algebra, but that's not it. That's not all that the subject involves. And so we're going to branch out into the study of what are called linear transformations now. And so we need to set the stage. So first of all, the set of all m by 1, I hate calling them matrices. They are matrices, but really I refer to them as vectors. These are column vectors. The set of all m by 1 matrices, which I'll refer to as column vectors, that is m by 1 column vectors, is denoted R upper n. So you've probably seen R, and you probably see the symbol R, which looks like this, and then there's symbol R2, that refers to the plane. R3 refers to three-dimensional space. More generally, what we have is the set of column vectors with m entries. Right? We call that R sub m. And so as a set, right, so it's the collection of all of them. So Rm looks like this. Column vectors, the collection of all possible column vectors with m entries, where each x sub I is a real number, right? That is the set Rn. So what that means then, right? I mean, oftentimes, and I think you've seen, right? R2 refers to the plane, and so we can depict the plane in this way, right? So where each point we view as a column vector rather than, normally we write it as x comma y with parentheses around it. But what I want to do is refer to each column vector. Right? We can think of that as a point in the plane also. Okay, so there's R sub m. Now, the next thing I want to talk about, everyone here has heard the word function and talked about functions. I want to define function in a more precise way than you do in calculus, but maybe not quite as precise if you take in Math 248, not quite as precise as I would define it in Math 248. So a function is a rule, and we'll give it a name, little f, that assigns to each element, say, little x, in its domain, and I'm going to use the symbol, I guess I'll use the symbol capital A. Well, is A a good choice? Yeah, I guess so. It's assigns to each element little x in its domain, capital A unique. I was debating whether I wanted to use a capital A here because I use capital A for matrices. So now I'm thinking this is a set, not a matrix. A unique element, which we will write as f of x in some set capital B. This set capital B is called the codomain. B is called the codomain. All right, so a function is a rule that assigns to each element x in its domain a unique element f of x in some set B. So a function, here's another way to say it, a function is a machine. It takes as input a little x and gives as output f of x. The set of inputs, that's called the domain. That's what I'm calling capital A. The set of outputs lives inside, we've got to put them somewhere. Set B, the codomain, is the place that we put the outputs. That's where the outputs live. The notation is like this. So when you see this, you read this, f is a function from A to B. The domain, arrow, codomain. And the schematic, the picture that you want to think of, so A is some set, and F is the machine that takes each input little x and spits out an output, and the output is little f of x. So you've seen lots of examples of this in calculus. So, for example, the function f from R to R, defined by f of x, oh nice, equals x squared. For whatever reason now the lights just turned out on me, so I'm going to turn them back on. Oh, some sort of motion detector just turned it back on, sorry. So what do we have? F of x equals x squared. Here's an example of a function. The inputs come from the real numbers. The outputs are also real numbers. So in this case, our domain is R. Our codomain is R. The formula that tells us who the outputs are is right there. F of x, the output, is given by the formula x squared. Well, let's try one more example that's a little different. How about this one? Let's give it a different name. How about little g from R to R2, defined by f of x equals, and I'll write it as a column vector now, cosine t over sine t. I can't use a t here, I gotta use an x. So it should be cosine x, sine x. So in this case now, the inputs, still real numbers, the outputs now are column vectors of this form right here. So here's another example of a function. Domain R, codomain R squared, and the formula, input is a real number, the output is an element of R2, a column vector. Now, our interest in this class is going to be in functions that go from, say, Rn to Rm. So we will be concerned with transformations, and this is a certain kind of function. So with functions, and I'm going to use a capital T for the name of my function rather than a little f. So we're going to be concerned with functions of the form capital T from Rn to Rm, and these are called transformations. There's a special case. So a transformation is a function whose domain is Rn for some choice of n, and whose codomain is Rm for some choice of n. So when the domain and the codomain are sets of column vectors, that function is called a transformation. One special case, so when m equals n, t is an operator. So it's just a special, when we say, let's consider the operator t, what we're saying is it's a transformation from Rn to Rn. So here's an example of a transformation. Let's do T from R3 to R2. And now I need to tell you the formula. So defined by T of, now the input is going to be a column vector of the form x, y, z. The output is going to be given by this formula right here, x plus y squared and y minus x plus sine of z. So here's an example of a transformation. The input is a column vector with 3 entries, which means it comes from R3. The output is a column vector with 2 entries, which means that it lives in R2. So, for example, let's say, well, let's just, so working the same example, what is T of 3, 2, let's just do 3, 2, 0. Well, let's see. So it's going to be the vector. In the top, it's going to be 3 plus 4. In the bottom, it's going to be 2 minus 3 plus 0. 2 minus 3 plus 0. And so what we get is the vector 7 minus 1. Okay, so there's an example of a transformation. Now, here is the key example. So, key example. Let's put stars around this. This is, I don't know, in some sense, the essence of linear algebra right here. So let's say that we have, so let's say if capital A is an m by n matrix, we can define, and I'm going to write it as T sub A, and this is going to be a transformation from Rn to Rm. Now I need to tell you the formula. So T sub A, that's the name of the function. Its domain is Rn, its codomain is Rm. And we're going to define this transformation by T sub A of the column vector little x. So this will be a boldface x in your book. I'm writing a little arrow over it. So T sub A of x is equal to A times x, matrix multiplication, this vector, this m by n vector, times the column vector x. This, right, so such a function is a matrix transformation. So that is the key example of the type of function, the type of transformation that we are going to be studying. Those are the ones called matrix transformations. So, yeah, let's try an example. So as an example, let's let A be the matrix 1, 4, 3 and 2, 0, 1. So then T sub A is going to be a transformation from R3 to R2. And it's defined by t sub a of the column vector, let's call it x, y, z, is equal to a times x, y, z, like that. So here's an example of a matrix transformation. And let's see how this actually works. So let's plug in a specific, an explicit vector now. So let's say that we do t sub a of 1, 2, minus 4. Okay. Now what that means is a, so that's 1, 4, 3, times 2, 0, 1, times 1, 2, minus 4. And let's see what we get. We're going to get, in our top entry, it's going to be 1 plus 8. 1 plus 8 is 9, minus 12 is negative 3. And then we're going to get 2 minus 4, so we'll get negative 2 in the second entry. Right? So here's our input right here. The output is right there. In general, so the general formula for t sub a goes like this. So what we're doing, so t sub a of the vector x, y, z is equal to matrix A, so that's a 1, 4, 3, 2, 0, 1 times x, y, z. And what that's equal to, that's going to be the vector, and it will be x plus 4y plus 3z. And then it will be 2x plus z. Right? So here's a formula that tells us how to associate to each vector in R3 a vector in R2. Right? Here's an example of a matrix transformation. Some more sort of special examples. The first one, so I'll say, so here's an example, and this one has a name. It's the zero transformation. Now what that's going to do is it's going to give or associate to each vector the zero vector. So it goes like this. T sub 0 goes from Rn to Rm. And how does it work? So it's defined by T sub 0 of the vector x. Let's write it as a column vector. So it'll be T sub 0 of the column vector x1 dot 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 x sub n equals the vector, and here there will be m zeros right there. Right, so there's an example of a transformation. That's actually a matrix transformation. How would you do that? You do it by multiplying by the zero matrix. There's also the identity operator. So another example, if I equals I sub n, so this is the n by n identity matrix. Sorry, I keep stepping out of the shot there. So if I equals I sub n, we have the identity operator. This would be, well, it would be T sub I going from Rn to Rn, defined by, well, it's the obvious thing here. T sub I of x equals I times x. Well, when you do the identity matrix times a vector x, you get x. So it's the identity, the input is x, the output is also x. That's called the identity operator. Matrix transformations have some nice properties, right? And I'd like to write these down. So let's call this a theorem. Properties of matrix transformations. So let's let capital A be m by n. So we've got an m by n matrix. Let's take a couple of vectors. So let's say u and v in Rn, and I also need a constant. Let's just call it r. So r, a scalar. A scalar, that's just a fancy name for a real number, a constant. Right, so we've got m by n matrix, a couple of vectors, and a constant r. First property, so property A, t sub A of the zero vector is equal to the zero vector. So if you input the zero vector, you get out the zero vector. Property B, t sub A of r times u. So if we do scalar multiplication, r times u, plug that into the matrix transformation, that's equal to r times t sub A of u. So this is nice. You can pull the constant out of the function operation, the transformation operation. And then part C, t sub A of u plus v is equal to t sub A of u plus t sub A of v. All right, so these three properties right here are nice properties of matrix transformation. And we don't need to prove every single one of these, but let's just see why some of these are true. The first one's obvious, right? I mean, if you do A times the zero vector, right, a bunch of zeros here, we'll have n zeros right here, right? The output is going to be, when you do matrix multiplication, 0, 0, a bunch of zeros, there will be m zeros in that column vector right there. Right, this one's pretty obvious. Let's look at, maybe I'll do part C and leave part B as an exercise for you. So we'll say B, you try. And I should have labeled this, sorry, that was part little a right there. So now part C, so what do we have? T sub A of u plus b. What's that equal to? Well, it's equal to A times the vector u plus b. Now, we learned a property of matrix multiplication. Remember, in the end, and I like to call them column vectors, but they're still matrices, right? These are both n by 1 matrices. We learned a property of matrix multiplication that tells us that we can rewrite this as A times the matrix U plus A times the matrix V, right? This was a distributed property of matrix multiplication. All right, now what is this? Well, A times U, that is T sub A of U. And what about A times B? That is T sub A of U. Okay, so that explains why those properties are true. And T sub A, or this is part B right here, the proof of part B, I'm leaving that as an exercise. It's essentially another application of one of the properties of matrix multiplication. Now, more generally, and in fact, I'm going to leave that part up right there. So a more general fact, and this is important. So more generally, if we have the vector A expressed as A1 times some vector x1 plus A2 times some vector x2 plus ... and we have A sub k times x sub k. Remember what we called this? We called this a linear combination, right? When we have constant times matrix plus constant times matrix and so on. Right, that's a linear transformation. A linear combination. So if we have this situation right here, then T sub A of our vector x. So imagine plugging this big sum into here. And what does it come out to be? Well, it turns out it will be A1 times T. You know what? In fact, I want to write out the steps of how this goes, just so you can see it. This is important. So this would be T sub A of A1x1 plus A2x2 plus dot 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 plus A sub k x sub k. Okay, now what does property C tell us? It tells us that you can split up an addition into two pieces. Well, if we're adding k different ones, property C tells us we can split that up into k pieces. T sub A of A1x1 plus dot 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 plus T sub A of A sub k x sub k. All right, so there's the first step. And then what does property B tell us? It tells us we can pull out each of these constants. So this is equal to A1 T sub A of x1 plus dot 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 plus A k T sub A k times xk. Right, so there's the steps. Now let me combine this. The way you want to think of it is this. T sub A of A1 x1 plus dot 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 plus A sub k x sub k is equal to A1 T sub A of x1 plus dot 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 plus A sub k T sub A x sub k. So that right there, I'm going to put that in a box right here. What it tells us is that matrix transformations behave nicely when it comes to linear combinations. So let's write it like this. Matrix transformations behave nicely with respect to linear combinations. Okay, so that's what that shows me. Okay, so we've defined this thing called matrix transformation. And now we want to talk about something very, very closely related. In fact, what we're going to find is that it's the same concept. But I'm going to just write this down as a definition. So definition, a function, and let's call it capital T, from Rn to Rm, that satisfies two properties, right? So it's called a linear transformation. This is a linear transformation if the following properties are satisfied. For every, let's get this right. So for every, say, vector u and v in Rn, and every scalar R. Right, so now I need to write down the properties that are satisfied. So property A, T, which order do I want to do this in? Let's do it like this. So T of u plus v is equal to T of u plus T of v. So there's property A. And then property B, T of R times U is equal to R times T. So a function, a transformation, right? It's a function from Rn to Rm. A transformation is called a linear transformation if it satisfies these two properties. Every time you plug a sum of vectors into your transformation, you can split it up as two separate pieces. Same thing, you can pull scalars out of the application of the transformation. If those two properties are satisfied, then you've got a linear transformation. From our previous theorem, it follows automatically that every matrix transformation is a linear transformation. Right? So from our previous theorem, that's the one that we called, what we call it, properties of matrix transformations. So from our previous theorem, we see that every matrix transformation is a linear transformation. Right, so if you look at that theorem, it tells us every matrix transformation satisfies these two properties. That guarantees us that matrix transformations are linear transformations. There are some important vectors, some vectors that I want to focus on in Rn. So we'll think like this. In Rn, define, and this is really just notation, shorthand for certain vectors. So I want to define bold-faced E1, that will be the column vector that has a 1 in the first position and zeros everywhere else. So it'll be 1, 0, dot, 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 0. Then there's E2. That's going to be a vector that has a 1 in the second spot and zeros everywhere else. So it'll go 0, 1, and then 0, dot, 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 down to 0. And you can keep going, so there's an E3. That will be the obvious thing, 0, 0, 1, 0, dot, 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 0. And you keep going, right? Eventually, we get to E sub n. That will be the column vector that has zeros everywhere except in the very last spot, it'll have a 1. So it'll be 0, 0, 0, 0, 0, 1. Okay. So these vectors, they're called the standard basis vectors. The E sub i's are the standard basis vectors for Rn. So E1 is called the first standard basis vector, E2 the second. In general, E sub I is the ith standard basis vector for Rn, and the collection, or the set, consisting of E1 up through E sub n. Remember, in your book, these will be bold-faced E1 up through En. This is the standard basis, so this is the standard basis for Rn. So this is just some shorthand notation and some terminology. But here's one thing to notice. So note that every vector, say x, and let me write it out. So x is the column vector x1 down to xn. In Rn can be expressed as a linear combination of the E sub i's. And that's really the point here, why we care about the standard basis vectors, is because every vector x in Rn can be expressed in terms of the standard basis vector. So how does that go? Well, x, which is x1 down to xn, is equal to x1 times the first standard basis vector plus x2 times the second one plus dot 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 plus x sub n times the last one. In other words, x is equal to x1 e1 plus dot 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 plus xn times e sub n. Now, I just want to remind you something from what we covered a few days ago in terms of matrix multiplication. So let's just say recall if x is equal to x1 dot 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 x sub n. Oh, how do I want to say this? Right. And let's write it like this. And capital A sub I is the ith column of the matrix A. Let's say of the m by n matrix A, then A times X. We talked about this, we didn't go into a whole lot of detail here, but A times X is equal to X1 times the first column of A. We did mention this. I think I wrote it as, I wrote the columns as C1, C2, and so on. It was somewhere around lecture, must have been end of lecture 3 when I discussed this. So A times X equals X1 times the first column plus X2 times the second column plus dot 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 Xn times the last column. So matrix multiplication, matrix times column vector can be expressed in this way. In other words, A times X is a linear combination of the columns of capital A. Now, so let's say now, suppose, let's call it capital T, and this is going to be a linear transformation from Rn to Rm. So suppose T from Rn to Rm is a linear transformation. And I want to define a certain matrix. So define the matrix in, who am I going to call it? I'll just call it capital A. So define the matrix capital A. And it's going to be the matrix whose columns consist of, so the first column is going to be T applied to E sub 1. So T applied to the first standard basis vector. And then the next column is going to be T applied to the second one. And you keep going, so we're going to form an m by n matrix whose columns are T of E1, T of E2, dot, 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 T of E sub n. So, right, so these are the columns. So there's column 1, column 2, etc. Right, there's column n. right there. Okay, so we've created this matrix. We start off with a linear transformation. I want to define a matrix A that looks like this. That's the outside of my frame here, so I need to keep that marked. Okay, so we define this matrix, and what's the point here? So now, let's just take a random vector. So suppose, or given x equal to x1 dot 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 x of n, let's observe that t of x. Well, now t of x is equal to t of, remember, x can be expressed as a linear combination of the standard basis vector, so this will be t of x1 e1 plus dot 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 plus x sub n e sub n. So here I've expressed x as a linear combination. T is a linear transformation, which means I can break this up. It satisfies the properties x1 t e1 plus dot 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 plus x sub n t of e sub n. If you have a linear transformation, it satisfies those properties. I call them properties A and B. That allows us to split this linear combination up in this format right here. Now, notice what this is. This is x1 times the first column of capital A. The next one, it would be an x2 t of e2. Oh, and I should have a little arrow over there. That would be x2 times the second column of my matrix A. And so on. This would be equal to A times x. From right here. And maybe, let me fill this in. So this really is x1 times a1, the first column of capital A, plus x2 times a2. Instead of skipping that step, let's put that in there. So xn times a sub n, the nth column of my matrix A. And this is equal to A times x. In other words, the formula for T can be computed by doing matrix multiplication, A times X. So, in other words, right, so this is, let's say it up here. So, in other words, T is equal to T sub A. And we should put some exclamation marks there. This is big. This is amazing. What is this saying? It's saying that every linear transformation is a matrix transformation. And remember, just a little while ago, we showed that every matrix transformation is a linear transformation. Now we have the reverse. In fact, we should state this, we can state this as a theorem. Let me write a little bit of terminology here. A, capital A, is the standard matrix of capital T. Okay, so now we can state this in a theorem. So say it like this, a function capital T from Rn to Rm is a linear transformation if and only T is a matrix. Transformation. That's amazing. So what this now tells us is that linear transformations and matrix transformations are one and the same. If you have a linear transformation, it can be expressed as matrix times vector. If you have matrix times vector, it is a linear transformation. And we can say a little bit more in this theorem, so let's say moreover. If T is linear, so if T is a linear transformation, then T is equal to T sub A. So this is going to tell us who the matrix transformation is, or who the matrix corresponding to T is. So then T is equal to T sub A, where, and let's put the A, we can put it right here, so where A is equal to the matrix whose columns are T of E1 through T of E sub n. This is a big deal. You don't need to put stars here, but I'm going to put some stars and some arrows, right? This tells us everything. It tells us this connection between matrices and linear transformations. Okay, let's do some examples now involving linear transformations. And all the stuff that we've learned so far. Before I do so, I need to point out the book uses slightly different notation, and the reason is to conserve space. So let's just say it like this. So note, the book usually writes T of X, Y, Z, etc., rather than T of column vector X, Y, Z. So what you need to be able to do is go back and forth easily between three tuple or triple notation and column vector notation. It's all the same thing, but if in the book, if you wrote column vectors all the time when you're plugging them into linear transformations, it would just take up so much more space. So to conserve space, it's written this way. You should be able to go back and forth between these two notations. Okay, so now some examples. Since I've got lots of space because I'm writing on a board, I'm always going to use the column vector notation, right? R sub n, R sub m, those are collections of column vectors. So, first example, let's say consider the function capital T, and we're going to go from R3 to R4, given by. So now I need to tell you the formula for this function. And so the input is going to be a vector, a random vector, with 3 entries, so x, y, z. And the formula is going to be a vector that has 4 entries, so it's going to go like this: x plus y, 2x plus y plus 3z, 2x plus y plus 3z. And the next one is going to be y minus z. And the last one is going to be x plus y plus z. Okay, so here's a formula. The input is a vector with 3 entries. The output is a vector with 4 entries. And then there's 2 parts to this problem. So the first one, I want to show that capital T is a linear transformation. And part B, once you verify that it's a linear transformation, then we know, we saw this theorem that says every linear transformation is a matrix transformation. So now I want to find the standard matrix. So find the standard matrix of capital T. That is, we want a matrix capital A so that T is equal to T sub A, the matrix transformation. All right. So for part A, remember there's two properties that need to be satisfied to be a matrix transformation. Let me get a little drink here. Two properties. So I need to show first, and I'll just remind you, so I need to show first of all that, say, T of U plus V equals T of U plus T of V. And then the second property, remember, that's T of RU equals R times T of U. So I'm going to show all of this in detail. So let's write, I need a couple of vectors here, so let's write, in this case, let's say U equals, let's use ABC here, and V is going to be the vector, some good letters here, A, B, C, D, E, F. Nah, I don't like that, D. Let's use X, I'm going to use X, Y, Z, that's fine. So I've got my two vectors, and so now I want to look at T of U plus V. That's going to be T of the column vector A plus X, B plus Y, C plus Z. Okay, now I need to follow what the formula tells us to do. Let's see, it tells us to add the first two entries. So that would be an A plus X plus B plus Y. Then we're going to have 2 times the top entry, so that'll be a 2 times A plus X, plus the middle entry, so that's plus B plus Y, plus 3 times the bottom entry, so that's plus 3 times C plus C. Is that right? 3 plus the bottom entry, yeah, C plus C. Then we're going to have, what does this say? It says second entry minus third entry. So that would be B plus Y minus C plus Z. And then final entry is going to be X plus Y plus Z. So that's add A plus X plus B plus Y plus C plus Z. Like that. Okay, so that's what the formula tells us. And now, there's properties of vectors. I'm going to use the distributed property all over the place to rewrite this. So let's see. Inside the parentheses, or inside the square brackets, I'm going to write this as A plus B plus X plus Y. Then I'm going to have 2A, I need parentheses here. 2A plus B plus C. No, sorry. Let's do this right. 2A plus B plus 3C plus 2X plus Y plus 3Z. Then I'm going to have B minus C plus Y minus Z. And then in the last entry, I'm going to have A plus B plus C plus x plus y plus z. Okay. Now, sorry, I'm standing out of the shot here, but here's what you get. And now, sorry, I'm gonna, even if I have to disappear from the shot, that's okay. My x's, sorry, I'm just gonna check my, no, that's okay. Okay. So now, I'll be standing out of the shot, you'll just hear my voice and see my hand moving. I'm gonna split this into a couple of vectors. So this is gonna be A plus B, 2A plus B plus 3C, B minus C, A plus B plus C, plus the vector x plus y, 2x plus y plus 3z, y minus z, and x plus y plus z. Here, all I'm using is properties of matrix addition. Right? I can take this matrix right here and split it into these two matrices. And then I'm just about there, and I don't want to erase this, so I'm going to erase what I have up there. So pay attention. So what I have is this stuff here, and I'm going to move right up, back up to here so I don't have to erase my problem. Okay, now this right here, this is equal to T of U, right? This is exactly what would happen if you put A, B, and C right here. It would tell you to write down this vector right here. So this is T of U plus T of B. So that tells us that it satisfies property A of linear transformations. Okay. So now let's check the second property. And that tells us that we can pull constants out. So now I want to look at T of, say, R times U. That's going to be T of the column vector, who's U? U is A, B, B, C. So it'll be R, A, R, B, R, C. And that's equal to, let's see, R A plus R B, 2RA plus RB plus 3RC. And then we're going to have RB minus RC. And then the last entry, RA plus RB plus RC. Okay, so that's what would happen if you plug R times U into this function. Now notice, I can factor an R all over the place. So this will be an R times A plus B. And this will be an R times 2A plus B plus 3C. And this will be an R times B minus C. And this one will be an R times A plus B plus C. Here now I can pull the R completely out of the column vector. So this will be an R times A plus B, 2A plus B plus 3C, B minus C, and A plus B plus C. And what's this? This is R times T of U. Okay, so that completes part A. Now we need to do part B, which is to find the standard matrix of T. Teaching like this is so weird, right? Because normally, when I work through this example, the next thing I do is say, any questions? And I can look around the classroom and I can see someone might raise their hand. Someone might have just a confused look on their face. We can stop, slow down, explain, and so on. So, obviously I can't do that in this setting. has to be done during office hours. So if you are confused, I know I said this in the email recently that I sent out, if you feel like you're missing something, falling behind, see me, come to the office hours or set up a separate appointment, right? I'm around lots and lots of times. I can set up quick meetings, Zoom is easy to use. We could do a 10-minute Zoom meeting. It's no problem, I can do this. So don't let yourself fall behind, stay on top of things. Okay, so we'll move on to part B of this example. And so that's find the standard matrix of T. How do you do that? Well, we go like this. T of E1. That's T of the vector 1, 0, 0. That's going to be 1, 2, 0, 1. T of E2. Right, so I plug in the second standard basis vector. That means T of the vector 0, 1, 0. That's equal to the column vector 1, 1, 1, 1. I'm just following this formula. Oh, I don't know why the light keeps turning out. There we go. And then I'm going to do this one more time. T of E3. So I plug in the third standard basis vector, and so that means T of the column vector 0, 0, 1. And that's equal to 0, 3, minus 1, 1. So, who is the standard matrix for T? It's the matrix whose columns are right here. And so it will be 1, 2, 0, 1. 1, 1, 1, 1. 0, 3, minus 1, 1. That's it. To find the standard matrix, plug the standard basis vectors in, write them out, and the columns in order will be the outputs that you get when you plug the standard basis vectors in. I'm going to do a couple more examples. So, next example. I want to show, so here we go, example, show that the transformation here, this is going to be T from R2 to R3. Defined by, and just, I normally use column vector notation just so you can see how the book does it. I'm going to write it down in ordered tuple notation here. So T of x, y equals, and the formula will go like this, x plus y, x squared plus y squared, and xy. So here's our transformation, our function. Show that this function right here is not, so funny looking n, is not linear. Right? So here's a transformation. Right? It's input vectors from R2, output vectors in R3, but it's not a linear transformation. Now the way to do this, well, actually there's a couple ways to do this. Let's do this one. So how do you show that it's not linear? You show that it does not satisfy one of the two properties that linear transformations have in their definition. Right, so that either part A or part B of the definition of linear transformation fails. So the way I'm going to do this, so let's let x be the vector, and I want it to be 1, 1. Then, if I compute t of 2x, that's going to be t of 2 comma 2, and that's equal to, so let's see what the formula tells me, it's going to be 4 comma, 4 plus 4 is 8, 4, so it'll be 4, 8, 4. While, if I look at 2 times t of x. Well, that would be 2 times t of 1, 1. So that will be 2 times, let's see, t of 1, 1 is going to be 2, 2, 1. And so what we get is 4, 4, 2. Right? So if you compare t of 2x versus 2 times t of x, you get different answers. They're not equal to each other. That counterexample right there shows us that it's not linear. All right, let's try one more example, and then we're going to wrap up this lecture. And this one goes like this. So I'm going to write down, I'm going to describe a certain linear operator. So let's find the standard matrix for a linear operator. Call it T. And this is going to be, now remember, operator means, now let's write it down. It's going from R2 to R2. Anytime that these superscripts match right here, it's just another word for linear transformation. So operator means, or linear operator means, linear transformation where Rn and Rn, the domain and the codomain, have the same superscript. So for the linear operator that rotates the plane, and I guess I want to go counterclockwise through an angle pi over 3. So rotates the plane counterclockwise. About the origin. Through an angle of pi over 3. So we're going to need a picture here. And hopefully everybody can see what happens, right? We're taking the entire plane, we're rotating it about the origin, right, through an angle of pi over 3. Now, how does this go? We want to find the standard matrix for this linear operator. Okay, to find the standard matrix, what do? You compute t applied to each standard basis vector. So in this case, we're in R2, there are 2 standard basis vectors. The first one, right there, is 1, 0. And the second one, right there, is, let's put it there, is 0, 1. Now, when I apply t, what happens? So this, let me actually label this. So there's E1, there's E2. Now what I need to do is figure out, okay, what is t of E1? Well, if you rotate through an angle of pi over 3, then t of E1, in fact, I don't even really need, yeah, that's okay. So t of E1 ends up over here. And who is that? Who is that vector? Well, it is the vector 1/2 over root 3 over 2. Yeah, I'm sorry, I started to make a second diagram, but we really just need to think about how it works in one picture here. And then the second one, all right, so here's another, there's an angle of pi over 3. And who is this vector right here? So t of E2, I don't want to crowd my picture too much, but there's t of E2, and who's that going to be? Well, if you rotate through an angle of pi over 3, that is going to be minus root 3 over 2 and 1/2. Right, so all I'm doing right here is unit circle trigonometry, right, to figure out who these two vectors are, right? When you rotate, who is this? If you like, who is this? This is cosine of pi over 3, sine of pi over 3. And then these entries right here, this is cosine of 2 pi over 3, because now we're going 2 pi over 3. Is that right? Yeah, 2 pi over 3, and this is sine of 2 pi over 3. So, who's the standard matrix now? The first column is going to be 1/2 root 3 over 2. Second column, negative root 3 over 2 and 1/2. Right? The columns of the standard matrix for a transformation, a linear transformation. Standard matrix gets columns obtained by plugging standard basis vectors into the transformation. Whatever you get, those are the corresponding columns. All right, that was fun.